Well, in this video, we're going to see how these hyperbolic trigonometric identities are derived. In particular, we'll show that both the hyperbolic sine of x and the hyperbolic cosine of x can be expressed in terms of exponential functions. I think this is worth explaining because the trigonometric functions we're already familiar with, like these, are usually expressed in terms of other trigonometric functions. For example, the most common identities, as you can see, are always written using other trigonometric functions. Of course, there are exceptions, such as this identity involving I, where I is a complex number. But as far as I know, over the real numbers, it's not possible to express the circular trigonometric functions in terms of exponential functions.
So, with that in mind, let's take a closer look at how the circular and the hyperbolic trigonometric functions actually work. Here, we have the unit circle, that is, a circle with radius 1. To summarize, what the trigonometric functions do is tell us the x-coordinate of a point moving along the circle. We measure that motion using a parameter called theta. Now, what happens if we do the same thing on a hyperbola?
If we want to describe the coordinates of any point on a hyperbola, we start with the equation x squared minus y squared equals 1. Notice that the only difference from the unit circle is the sign, and that turns the circle into a hyperbola. Now, just as before, we'd like to use something similar to the trigonometric functions to describe this point. Suppose we draw a line segment from the origin to point A, and instead of using the parameter theta, we'll introduce a new parameter that we'll call t. We'll also define a similar function. This time, we'll add an h to indicate that it's the hyperbolic sign. So the hyperbolic sign of t will be equal to the y-coordinate of the point.
At this point, we can't really say that t is an angle. So then, what exactly is an angle? Let's take a quick look. If you open almost any geometry or trigonometry textbook, you'll find that theta is defined as the arc length s divided by the radius. But there's another way to define theta, in terms of area. Specifically, theta is equal to twice the area of a sector of the unit circle. The gray region shown here is a circular sector, so its area is simply theta divided by 2. In other words, theta tells us how far this imaginary line segment is from the horizontal axis, or the x-axis. But on the hyperbola, thinking about how far the line segment OA is from the horizontal axis doesn't really help us describe the point or its coordinates. So mathematicians came up with a very clever idea. Instead of thinking in terms of angles, they thought in terms of areas. Depending on where we choose the coordinates of the point, we can always construct a region whose area is equivalent to the area of the circular sector.
If that isn't completely clear yet, imagine a triangle with area A and a hexagon with exactly the same area A. Their shapes are different, but their areas can be identical, depending on their dimensions. So we'll define t to be twice the area, which means that the area itself is t divided by 2. And that's really all we need in order to understand the hyperbolic trigonometric functions. We'll define the hyperbolic sine of t, so that when we evaluate it at any real number t, it returns another real number, corresponding to the y-coordinate of point A. The difference is that for the circle, cosine of theta gives the x-coordinate, or equivalently, the adjacent side divided by the hypotenuse. Here, however, the hyperbolic sign will be given by a function, which is exactly what we're about to derive. This function will compute the y-coordinate of point A. Likewise, the hyperbolic cosine of t will compute the x-coordinate of point A. So all that's left to do is calculate that area using an integral.
To make these two areas equivalent, we need to integrate this function up to point A, which we already know is the hyperbolic sine of t. We also need the base, which is the hyperbolic cosine of t, and we'll soon see why. Now, if we rotate the hyperbola, of course, you can do this mentally, but this way it's much easier to visualize. We can work with differentials of y, and then subtract the area under the line segment. Since the equation of the hyperbola is x squared minus y squared equals 1, we'll work with the unit hyperbola, just as we worked with the unit circle. So let's set up the integral. The limits will go from 0 to the hyperbolic sine of t. For the integrand, we first solve for x, giving us the square root of 1 plus y squared. From this, we need to subtract the line segment. But remember that earlier we drew a triangle. It's much easier to subtract the area of a triangle than to find the equation of that line segment. Now, we know that the area of a right triangle is 1/2 times the base times the height. We've already identified those quantities. The base is the hyperbolic cosine of t, and the height is the hyperbolic sine of t. We then set this equal to theta over 2, forcing both regions to have the same area.
And that's all we need to finally derive the identity we saw at the beginning of this video. As you'll notice, this integral is actually quite straightforward if you're comfortable with integration. In fact, the only part we really need to solve is the expression shown in green. I just noticed that I forgot to write the differential dy here. Since that's the only area we're actually integrating, the differential belongs there, not in the area of the triangle.
Now, to evaluate this integral, I'm going to use trigonometric substitution. The tangent of the angle theta relates the two sides of this triangle, so I'll substitute y equals tan theta. Likewise, I'll replace dy with the derivative of the tangent function, which is secant squared of theta d theta. If you're not familiar with what I'm doing here, you can check out the integration playlist on my channel. One mistake I often see is changing the limits of integration immediately after making a substitution. In this particular problem, however, this won't be our last substitution, so changing the limits at this stage isn't really convenient. It makes the calculation longer and can easily lead to mistakes. In fact, there are several videos on YouTube covering this derivation, and many of them end up with errors because keeping track of the changing limits becomes rather tedious. It's also worth thinking about why the limits have to change in the first place.
When you change variables, you're changing the graph as well. If you plot the original expression on a graphing calculator, you'll get one curve. If you plot the transformed expression, you'll get a different one. In fact, a hyperbola. That's precisely why the limits must be adjusted, just as we did at the beginning of the video, so that these two different geometric regions still represent the same area. Anyway, getting back to the derivation, I'm not going to evaluate the definite integral directly. Instead, I'll solve the corresponding indefinite integral first, and then recover the original variable afterward. To simplify the integral a little further, let's use a well-known identity. The secant of theta is equal to the square root of 1 plus the tangent squared of theta. Multiplying this by secant squared of theta d theta, we end up with secant cubed of theta. Now, this integral can be solved by integration by parts, which would require yet another substitution. And that's exactly why I prefer working with the indefinite integral instead. Since I've already solved this integral in another video on my channel, this time I'll simply use a standard table of integrals. Right now I'm using Purcell, and formula number 37 gives the general expression for the integral of secant raised to the nth power. Applying that formula, we obtain the following result. Secant theta times tangent theta plus the natural logarithm of the absolute value of secant theta plus tangent theta, all divided by 2 plus a constant.
Now, remember that the original integral was written in terms of y, not in terms of trigonometric functions. So we'll use this triangle once again to recover the original variable. The secant is the hypotenuse, which is the square root of 1 plus y squared, divided by the adjacent side, which is simply 1. Likewise, we can immediately see that the tangent of theta is y, just as we established earlier. Substituting these expressions back into the result gives us y times the square root of 1 plus y squared. We do exactly the same thing in the logarithm. The secant becomes the square root of 1 plus y squared. The tangent becomes y, and everything is divided by 2, plus a constant. However, we can ignore the constant because we're evaluating a definite integral with limits from 0 to the hyperbolic sine of t. Now we can evaluate the integral. Remember that its value represents an area, and that area is still being subtracted from the region shown here in pink.
Now we need to evaluate the hyperbolic sine of t wherever we see y. So evaluating the hyperbolic sine in this expression, we obtain the following. We simply replace every occurrence of y with the hyperbolic sine of t. Now let's evaluate the lower limit. Replacing y with 0, we immediately see that this entire term becomes 0. And here, we get the natural logarithm of 1 divided by 2. Since the natural logarithm of 1 is 0, this entire expression also evaluates to 0. So there's really no need to write that part. At first glance, this expression looks rather complicated, but we already know several identities for the ordinary trigonometric functions, and the same is true for the hyperbolic trigonometric functions. So we can immediately recognize that each square root is simply equal to the hyperbolic cosine of t. Now it's clear that we have two expressions that are exactly the same, except that they have opposite signs. So when we subtract them, those terms cancel out. We can also cancel the factor of 2. Remember that theta over 2 has remained with us all the way to this point, because that's exactly how we defined it at the beginning of the video. At this stage, we've essentially accomplished our main goal, which was to show that the hyperbolic trigonometric functions can be expressed in terms of exponential functions. The only thing left is to eliminate the natural logarithm.
Taking the exponential of both sides, we obtain the following equation. At this point, however, we have everything written in terms of x, while on this side everything is written in terms of t, and here it's written in terms of theta. But remember that theta is simply a real number, just like t is a real number. Let's also recall what theta actually represents. Earlier, we defined theta as twice the area, and in exactly the same way, we defined the parameter t as twice the area. So it's clear that t is not an angle. In fact, using a different symbol from the very beginning would probably have been a better choice. Taking the exponential of both sides, we obtain the following equation. At this point, however, we have everything written in terms of x, while on this side everything is written in terms of t, and here it's written in terms of theta. But remember that theta is simply a real number, just like t is a real number. Now, by adding and subtracting these two equations, we obtain twice the hyperbolic cosine of t and twice the hyperbolic sine of t, respectively. From there, all that's left is to solve for the hyperbolic cosine and the hyperbolic sine, giving us the identities we wanted to prove.